So the last section that we'll cover in chapter 6 is on the central limit theorem, a very important theorem in statistics. And let me try to give you an idea of what this theorem is about using an example of a fictional population of bunnies or rabbits. So I fictional because let's take a look. It says, suppose for a certain type of bunny, weights are normally distributed. So we have a bell curve with a mean of 25 pounds. So these are very large rabbits, and that's why I say fictional. So a mean, we're going to write the parameters of the distribution. So these bunnies on average weigh 25 pounds. So we know on a normal distribution, the mean would be at the center of the distribution. So most bunnies are average, and in this case, we're going to picture a 25-pound rabbit. Now, not all bunnies are 25 pounds. There's variety described by the standard deviation. So sigma, the population standard deviation of 4 pounds, tells us there is a spread to these rabbits. So though most bunnies are going to be around the 25-pound mark, so there's our average. There are occasionally out there, you'll find a really tiny bunny, much smaller, or you'll find a rather large bunny, but the extremes are less likely, and that's what makes a bell curve. So let me just first deal with picking a rabbit at random. So I'm going to just label the axis here. So X would represent the weight of a rabbit. And what if we randomly pick a rabbit or bunny, and we'd like to know the probability it weighs between 21 and 29 pounds. So we're looking for the probability that X, the weight of a rabbit, is between 21 and 29 pounds. So this brings us back to using our normal CDF function. And we have a lower bound of 21, an upper bound of 29, and our mean mu 25, and our standard deviation 4. All right, before I enter that into the calculator, I just want to come down and show you this graph drawn to scale. So the normal curve, the one I have here in blue, is my graph with a mean of 25 and a standard deviation of 4. So this graph, so this is the graph of X. So individual rabbits. These are individual rabbit weights. All right. And we know the mean, the center, was 25. And my lower bound and my upper bound here, 21 and 29. So lower bound, upper bound. And that would correspond to this area that's shaded with these vertical lines. And we will check out that value using normal CDF. So normal CDF, 21 to 29, with a mean average 25, standard deviation 4. And that's giving us 0.6827. So 68.27% chance that if you randomly picked a rabbit, it would be between 21 and 29 pounds. All right. So the new part that will get us to what we call the central limit theorem is that rather than considering X, one of these rabbits, we're going to take a look at sampling rabbits. And in particular, I'm going to talk about taking a random sample of 5 rabbits, bunnies, from this population. So for example, here's a group of 5, here's another sample of 5, here's another sample of 5. So what we'll do is think about randomly picking 5 bunnies and continuing this process, pick another 5 bunnies, pick another 5 bunnies, and continue to look at these groups of size 5. Now, what we're going to consider is rather than the weight of an individual bunny, we're going to take a look at the weight of the sample. So remember, sample mean is X bar. So we're going to pick 5 bunnies and find the average of the group. Pick a different 5 bunnies, find the average of the group. Pick a different 5 bunnies, find the average of the group. So in the central limit theorem, we look at the sample mean, and then we're going to talk about how it relates to the original population. So to have this make some sort of sense to you, let me take this example. So back in our original population, there are large bunnies, but there's not a lot of them out here in the right tail. So I'm going to make up a number here. The average bunny is 25. And let me just say that this very large bunny weighs 35 pounds. So he's 10 pounds above the average bunny. All right, but rather than considering him as an individual, what if he gets included in a sample? So that rather kind of large bunny in the background, let's say that that's the 35-pound bunny. So for this particular example, let's say that here is the data. We end up picking the 35-pound bunny at random from the population. But remember, we're going to continue to pick 4 more bunnies. And most bunnies are around the average. So while we may get this unusually big bunny, most likely the remaining bunnies would be closer to that average bunny. So the average was 25. So let's just say one of those bunnies is 25 pounds. And then maybe we get one a little above average, 26 pounds. And then maybe a little below average, 24 pounds. And then for my 5th bunny, let me go ahead and say 25 pounds. So this 35-pound bunny stood out as being quite different than the average. So that bunny is quite different here than the average. But what happens if that bunny gets included in a sample? So in this particular example, when we take the 35 as part of the group of 5, I'm going to average those 5 numbers. So if I take the 35-pound and add 25, 26, 24, 25, so I'm going to average these 5 numbers. So I'm going to add those 5 numbers and divide by 5, giving me an average of 27. So X bar, this average is 27. So the point here is that as an individual, that bunny is quite different, 10-pound difference. But when that bunny was included with other bunnies from the population, these smaller numbers in the 20s kind of balanced out the 35, and we're averaging 27. So the sample mean is only a 25 to 27. X bar is only a 2-pound difference, whereas the bunny as an individual was a 10-pound difference. So what the central limit theorem says is that when we look at group averages, they tend to vary less than individuals. So when we say tend to vary less, we mean tend to vary less from the mean. So an individual has a higher tendency of being different than an average has a tendency of being different from that mean. So that's the idea of what we call the central limit theorem. So the sample means have a bigger tendency to be close to the actual mean of your population. So let's talk about how the shape of the graph changes when you're looking at sample means. All right, so first we're going to indicate our sample size. So in this case, we took a look at 5 bunnies. And then it says, what are the parameters of the sampling distribution of the mean? So rather than the original data, this second graph, so rather than individuals, what we look at are all of the possible sample means out there if we randomly picked 5 bunnies. So I had pictures of these 3 possibilities, but if we continue to look at every group of 5 bunnies possible and we graphed the means of the samples, this is what we call the sampling distribution. So sampling based on samples, sampling distribution, and the characteristic that we're looking at is the mean. So sampling distribution of the mean. All right, so parameters. So the population mean, if we're looking at the sampling distribution, so my subscript X bar, well, the graph will still have the same center. So the mean of the sampling distribution is the same as the mean of the population. That part doesn't change. What changes is there tends to be less variation when we look at the sampling distribution. So what we're going to see is these bell curves are going to start having more of their area towards the center of the graph, and therefore they're getting taller to accommodate the tails coming in towards the center. So we're going to see less variation in this graph. So the standard deviation is the measure of variation from the mean. But when we're looking at the graph of the sampling distribution, this number will be smaller than sigma. So the formula for it, it's the sigma from the original population. And the way it gets smaller is we divide it by the square root of your sample size. So in this case, the original population had a standard deviation up here. So the standard deviation was 4. And now we're going to divide that by the square root of n, our sample size, which was 5. So I am not going to approximate this when I use this value, but I'm just going to show you here that they gave that value approximate 1.7889. So the original population was measured with a variation of 4 down here. So the original sigma was 4, so that's my wide bell. But if we're looking at the graph of the sampling distribution of the mean, that spread has gone down. So there's less spread, the bell becomes more narrow. And so it's going to be more likely that your X bars will be close to 25 than it was for your individuals to be close to 25. So just as my last comment here, it would be more unusual to get an average of 35. That would be very strange. An average of 35 would mean that these values would probably all be towards this high end. That would be unusual in a random sample. Usually what happens is that you're going to get a mixture of values. So some around the mean, some higher, some lower. But these big values, even if they exist, like 35, when you put them in a group, an average, that number, the 27, so that average tends to be closer to the 25. So the bell curve tends to center more on that average when we're looking at samples. All right. So the question is, if we're looking at a sample of 5 bunnies, let's find the probability that the mean of the sample, so X bar, is between 21 and 29 pounds. So 21, and now not X, but the mean of the sample, X bar. What are the chances that value is between 21 and 29 pounds? So we can see on the graph that more of that graph is between 21 and 29 pounds. And we'll show that in comparison here by using normal CDF. So let's do our area or our probability, normal CDF. So 21 is our lower bound, 29 is our upper bound. Our mean is 25. The thing that changes is our sigma. So the sigma for the sampling distribution is the original sigma, but we divide by the square root of 5. So we just want to enter it like that, and that way we'll make sure our answer is as accurate as we need it to be. So normal distribution. So normal CDF in this case, lower bound, upper bound, and the mean. And then 4 divided by the square root of 5. All right. So we're getting a much bigger probability now, 0.9747. All right, so there is a 97.47% chance if you picked up 5 bunnies that they would average somewhere between 21 and 29 pounds. So it's going to be much less likely to get extreme values when you're looking at the sampling distribution. And that is essentially the idea of the central limit theorem.